Just everyone, so that you know, this meeting is being recorded. If you have any objections to that, please reach out. But I don't have a whole lot of preamble here. Our speaker is Luis Lopez, who has done some really excellent work from NSIDC, working on a library called earthaccess that makes things significantly easier to access our Earth science data holdings in our various APIs. So without further ado, I'll turn things over to him.
Hi. I think Amy will start the presentation. So hi, everybody. You'll hear me talking a little later.
Great. And I'm going to throw the slides link into the chat, and I'll go ahead and kick things off. Hey, well, thank you everyone for joining today. I do want to acknowledge beyond Luis Lopez, our other co-presenters. So Luis from NSIDC DAAC, Aaron Friesz from LP DAAC, and Qiusheng Wu from the University of Tennessee, and also Leaf Map creator, will all be doing some demonstrations a little later on today. And I also want to acknowledge Matt Fisher from NSIDC, who also contributed here, but is unable to join us today. So I'm going to kick things off before we jump straight into explaining what earthaccess is and what it can do. I first want to start by framing the problem that we're trying to solve. And the first is data accessibility. So this is kind of a silly tweet, but probably resonates with a lot of you. But in particular, we wanted to frame kind of this data accessibility problem in the context of open science. And really where we truly can't enable open science if we don't provide these easy to use workflows for researchers to reproduce their workflows in an inclusive and efficient way. Of course, we know that moving to the cloud has added this additional layer of complexity and kind of adding this whole new kind of ecosystem and tool set that can be challenging for users to learn. And so going into a little bit more detail, and this is pretty well established at this point. I don't think this is really news or needs a lot of explaining. I think we all very much live and breathe kind of this large ecosystem of these complex and disparate APIs that we all support together. So we have Earthdata login, we have the common metadata repository, and again, with cloud kind of adding this sort of new variable and this new kind of tool set to their workflow to learn and understand. And not to say that these components, are faulty. Like if anything, they're extremely rich and robust APIs. But with that also kind of comes complexity, particularly for our end users and our scientists who, can't just dive in with that expertise as software engineers. And so this figure from Patrick Quinn from a while back now, this really highlights one of those more complex workflow steps, which is authentication in the cloud in particular. So we know that this has been a particular pain point for end users. Obviously, there's sort of a latency element to this, but especially, again, in that context of cloud adoption, this is challenging, particularly as we start to learn how to bring those workflows into the cloud and to work with IO clients. And we see this a lot, particularly in like a Python kind of ecosystem, when we have to authenticate against those S3 credentials. And again, this poses a lot of challenges. This is one in particular just to sort of highlight. And so, here comes earthaccess, enter earthaccess. And really the code example at the bottom left here, like this is really all you need to see or know if you were to take something home today. In a couple of lines of code, right, you can get from authentication, search, and opening directly within sort of your Python-based workflow. So the library handles authentication with NASA EDL. It supports, you can see that in line 4, it supports several strategies for that, including direct credential input, utilizing netrc, environment variables, etc. And then that next results line allows you to search. In this case, this is an example searching directly by the DOI of a particular data set, again, abstracting that CMR API into something more user-friendly. But I think it's that final line 12, that final line in this example that I think is really the most powerful. And also at the top, the fact that we're only importing these two libraries in Python, importing earthaccess and Xarray. But that final line, one, you can simply point Xarray to your earthaccess results in a single line, but also the same code will work no matter if you are running in the cloud or not. You don't have to kind of figure out or change or modify your code or workflow. So right there, we've really reduced that complexity and helped to reduce those cloud adoption barriers, I think, in a really big way. Okay, but something that's undoubtedly very special about this library and something that we did want to highlight front and center is the community component of earthaccess. And in order to kind of walk through that, we thought we had kind of to start with this question of like, why now? Like, what's brought this library to fruition? Or in other words, like, what allowed us or enabled sort of, this library from getting from Luis's brain out there into the public and to be kind of expanding and progressing so rapidly. And it really all started with NASA Openscapes. Hopefully this is familiar, I would hope, to most of you by now. NASA Openscapes is in its 3rd year. It's grown into a very large mentor team at this point across almost every DAAC, with this fundamental goal of helping researchers migrate to the cloud. And so essentially, we were able to learn from our cross-DAAC hackathons and tutorials. And so starting off, one of our big events that we led way back in 2021, this cloud hackathon, we were able to present what we were able to, show and demonstrate at that time. And we got a lot of feedback as we presented this. It's this complex tool chain. We're working with these complex APIs to really perform what should be simple tasks. And so again, we were able to learn and respond to those pain points. And just really in like a year and a half or so, you could see at the top, right, Luis presenting what was then called Earthdata back in 2022. So really just kind of a year and then a year and a half. The bottom right, where we started to get feedback on earthaccess from our scientists who were involved in our 2022 Openscape Science Champions program. We took that feedback and responded directly to produce something that, again, was really truly user-driven in terms of that feedback and how to make those workflows easier. But having that space within Openscapes to be creative and innovate within the mentor framework is what really has enabled us to develop the library as, again, user-driven, but also truly community-owned. So you can see this in terms of kind of our ratio of outside collaborators who directly contribute. The repository lives in the NSIDC organization. We have this large and broad range of maintainers across multiple DAACs and Openscapes industry partners who can collaboratively commit, review, and merge code. And this cycle at the bottom, this is not novel or new by any means in terms of issues and discussion being raised in GitHub, then having that maintainer group triaging and responding in a collaborative way, and then that collaborative reviewing and merging. Again, not novel, but at least for this library, it's really allowed us to progress quickly and make something, again, that's truly user-driven, but also user-involved and contributed. And you can't really see that in the breakdown of the commit history in the top left, but I think just seeing that sort of momentum and expansion of those commits, I think really speaks to this as well and shows how much momentum is here. And these are just kind of ending this section of the talk with just a few examples of interactions that have brought us joy. I think the top, this issue where we are labeling these good first issues for people to contribute to. Like, this is working really well. This is a user who's a postdoc at the University of Washington, has really no prior involvement here, but thought, hey, like this, I could take a crack at this. Could I be assigned to it? This person has also been involved in Opera and working with Opera and also the upcoming NICER mission. So this is really, really great to see. And then also, you know, kudos that we've seen across like our international user community. And then on the bottom right, this was great discussion and kind of follow on the X platform from the Earthdata article that was published, or the Earthdata article that was published about earthaccess, and working with this user on their X-ray workflow to get them seamlessly chugging along using earthaccess. So with that warning, we're going to switch now into kind of a section of, and really just to showcase earthaccess and a few different kind of earthaccess in action examples here. And actually, I think we'll kick things off back over to Aaron, maybe not as much live demo, but then we'll switch over to some live demos. So you've been warned. And with that, I'll kind of keep sharing, but I think I'll hand it over to Aaron next to talk about data use resources at the LP DAAC.
Yeah, so no live coding here. There's much cooler stuff to show later on. So I'll get through our section quicker. So this is just kind of provide a DAAC-centric, I guess, view of earthaccess and how we've been leveraging it. Next slide, Amy. And so this is kind of the old way of doing things. At least I'm pretty sure a lot of your scientists would be recognize a lot of this code. All of us had kind of a different flavor of this, but I mean, the trouble here is that you're going outside Python to create this netrc file. You're taking input and shoving it into that file, and sometimes it worked, sometimes it didn't. So this was a very, I guess, difficult thing to overcome, specifically in like workshops. And even when you were just kind of handing this off to users for your different resources, hoping that it worked and not real or understanding what was going on their personal devices when they were having problems, it was very hard to kind of troubleshoot. And so this kind of was kind of the start, and then going into the next slide, Amy. This is now what we have, and so from a workshop standpoint, this is no longer anything really that we need to worry about. We just say run this line of code versus, hey, go out and get this script, run that script. Hopefully you have the right read-write access to that script or the document that it gets created. So this has really taken a lot off the shoulders of users, a lot off the shoulders of DAAC personnel who host and do workshops. And I think it's really kind of made it a lot easier to get started with the data. So not only, I mean, does this kind of tackle the kind of authentication of data that you're accessing as you would historically, it also takes into account the S3 credentials as well. And so that could have been a very difficult thing to overcome, but earthaccess has really kind of helped us out there and made it a much more streamlined process. Next slide. The LPDAP has started adopting and integrating it into all of our tutorials. So we're trying to set everything up so that you can run this in the cloud or out of the cloud. And with earthaccess, it makes it very easy to make that switch. So all of our HLS tutorials have taken it up. Every emit tutorial that we've created now has it included, and we had some interesting tutorials that leverage the search capability and the access capability in earthaccess as well, finding these concurrent kind of overlaps of scenes, which interestingly enough has been kind of added to earthaccess as kind of a new feature, being able to visualize your results, not necessarily the data, but at least the footprints of the data. So I think there might be some highlights of that later on. But I mean, in short, really, the LPDAAC has really just jumped on to the earthaccess train, and it's been really good, and has made a lot of scientists' lives easier with regards to how to authenticate against our data. So that's all I got.
Great. Thanks, Aaron. I think I will stop the share and hand things over. Actually, yeah, Luis, do you want? I don't know if you want to say a few words, jumping into kind of a cloud-based workflow demo example, and then I can stop the share.
I'll start sharing my screen.
Great.
Can you see my screen?
Yeah, I can see it.
Perfect. So yeah, warning, this is a half-live coding demo, so things can go wrong and will go wrong. So I have my notebook rendered already. I'm going to talk a little bit about an aspect of earthaccess that is not well known, but I think it will be the most powerful feature of earthaccess, along with the authentication, and that is the access patterns that it allows us. So I'm really excited about the future of the library. And so warning and disclaimers, I use the imagery that we use at Openscapes, and contains a lot of Star Wars images. So I think it's appropriate. It's The Force Awakens. And other disclaimers about, all the things that I say are my opinion, not the employers. And a lot of this work, it's still experimental. So what I'm going to show you, it won't be available in earthaccess for, say, a month or two, or who knows. But I hope you get the point. And lastly, I'm gonna use memes and some pop culture. So in the cloud era, what can earthaccess do for us? So, the authentication part of it, that's very important. But the other relevant part, I think, of the library is like it can help scientists to streamline their workflows. And it's in a very good position to do that, because it's the interface between all these ecosystems, the Pangeo ecosystem of Python, and what we do with the APIs at NASA. So we have 4 points that are quite relevant to the cloud. One is the one that you know already, which is just accessing the files, right? Like I want to open a file, don't want to think about authentication and serializing that. That's in the cookbook examples, what everybody knows. And then there are other features that are like, this one is already available, the catching with Qiusheng. So Qiusheng is a library that, if you haven't heard about it, I think is very relevant and very important. There is a demo of this feature that was shown at the DAAC demo day in August. There is a link. I'll put the link to the notebook as well after the presentation, and you can watch that. But what I'm going to present today, it's a couple features that are like are going to become very relevant for the cloud. So one is smart access, and the other is scaling workflows with DAAC. So once that you have your workflow, your scientific workflow, how can earthaccess make it simpler so you can like scale to like, I want to do it for real this time? As you know, it's very simple. We don't import a lot of libraries. We're talking about Python and the Pangeo ecosystem. So we have our login. In this case, I'm using a data set from NSIDC. It's called, I don't know if you know the ISAT mission. I'm gonna put my, probably you know are familiar with that, but it's a LiDAR in a satellite that has a lot of different important data sets, and the data set itself is kind of complex. So it's kind of known for not being easy to work with, especially in the cloud. So what earthaccess can do is like, we can search for CMR, we say the short name, and we say, I want the data that it's in the cloud. So this distinction is important because some of the archives are duplicated in the DAAC in the cloud. Eventually, that will be all cloud, but you can make the distinction here. Earthaccess allows us to pre-visualize some metadata from CMR. Another disclaimer, we're not downloading anything here. Like, we're not going to download files in the whole presentation. So so here I'm sorting my results from by size. So for this search, I have everything from for what other would be like big data files to like 3.5 and gigabytes of HDF. And I'm borrowing something from from Ryan Abernathy when he talks about cloud, right? Like what cloud native workflows mean, right? Well, it could mean different things, but one of the core parts of cloud native workflows is that we don't replicate the archive. So what that means is that when we are accessing data, it's not like we copy the whole archive to our personal bucket, right? Like normally this is what happens. You open a store, and I'm using SAR as an example. It could be Cox from HLS or something. And then you do your analysis in place, you run your workflows, and we live happy ever after. But in our case, most of our data is not in SAR. There is some adoption now, but it will take time. And so what we need to do something with that. We cannot say to the scientists, and that this frustrates me a little bit. Like earthaccess gets you to the point that you can handle the authentication. It opens the file or downloads the file if you want to do that. But then things get slow there. So the thought is that scientists, researchers will do the analysis in the cloud. It'll be faster, but it's not fast enough. So I'm still frustrated by this. Let's do something about it. So this is more or less what you will do. You open the file. I'm opening a file that is the smallest on that list, and it's 0.3 gigabytes. And now the problem, right? You try to open it with XRA and the typical stack. I'm not using anything particularly different from, like, you can use GeoPandas or another Python library, but XRA is kind of like a common library for this. And can you see, just opening one granule and getting the data that I need, it took 12 minutes. I'm out of region, by the way. I'm not going to do in-region analysis in this presentation, which will make it a little faster, but it won't be that fast. I think it's like 5 minutes when you are in region or something like that. So now we need to use the force. And this is going to be a very similar approach, but earthaccess, because we know some stuff about the data, we're going to do things a little bit different. So the first thing that you might notice if you have used earthaccess is that the color changed. So now it's purple. Well, that's not the point. Now I'm going to open the same archive, same data granule that took 12 minutes. And I'm in my laptop. I'm not using the cloud, not using one of the hubs. And this is not a totally cloud optimized HDF, which will make things even more efficient. And then at the end, I'm going to compare if what I got from doing the normal way to the new way that's coming, it is the same data, right? Because that's what it should be. So it took 30 seconds. This approach, it's possible because earthaccess knows a little bit about the metadata in the data, and it can do smart things with the caching. So now that we have the information in our memory, we do the calculation, the assert should pass. And if it doesn't pass, well, it passed, okay. So recap, what have we done and what earthaccess will be able to do? And this is the important part. We open the file as usual. We interface the Pangeo ecosystem with NASA holdings. We didn't have to worry about authentication and all, but it took forever. Now, with these smart capabilities, we did it faster. If we extrapolate this to the cloud, it will be even faster. But this is the relevant part. And I put some bibliography here for people that are more into the technical details. But one important thing is that we just opened one granule. And as it stands today, we are egressing 10 times the data that the granule is. With earthaccess, we are egressing only a third. And as I said, This is because the cloud, the data is not cloud optimized. It could be even more efficient and faster if we were handling with cloud optimized HDF, which, by the way, there will be a talk at SciPy if you're interested. And why this is important, right? Well, this is from the annual report from ESDS about the egress in size and number of files, and it's going up. So with new missions, egress will grow, and I heard that AWS is not charging free for egress. So I think it'll be really important for cost savings to use this approach that is more native, and earthaccess can help with that. So just that, I think it's really, really, really important to keep working in this kind of stuff. Now, what this enable us? Now that we can have smart access patterns to mission data, well, now we can do the fun stuff. And all of that to say that the important thing is not the library. The important thing, well, it could be important, but the important thing is the science. And the personal motto for earthaccess is that scientists shouldn't be, taking hours and hours of their time thinking about how they are going to access the data or thinking about all of this. Most of them are not software engineers, and even us that are software engineers, we have issues with the APIs and the services that we use. So for this, I'm going to quickly show an analysis that I did. It is the same code. I didn't change anything. I'm doing it in my laptop. I'm going to use Muir, which is known for having like kind of big data. Each granule is like 500 megabytes or so. So locally, I'm doing 10 years, and I'm going to just ask the question, what is the mean temperature in the Great Lakes around Christmas? And then I'm going to do the same, but I'm going to do it a little bigger, and that is 20 years for all of the month of December. And as you can see, I'm not using SQS or step functions or lambdas that we can use. I mean, like if a scientist has that like lower level in terms of the API knowledge, and that's what they feel like comfortable doing, that's fine. But most of us, we like a couple lines of code or something like that. So I'm searching. This is something that, again, it should be simplified within earthaccess. It's a seasonal search. I'm just interested for a particular, this is supported in CMR, kind of obscure, but it's supported that you say, I want only from this day to this day for every year. So I'm talking about 1/4 terabytes of data. This is not simple to do it in our laptop. So that's what I'm using the cloud. And I'm using a service that is called Coil that does provisioning for DAAC services. And I'm quoting myself. You have to see it and run it to see like, oh, this is cool. This function is basically what it does is just like getting the granule and creating an aggregate using X-ray. A lot of the code, or half of the code, can be half, because it's just tracking of the IO stats, because I'm interested in that later. And again, if we run this code in our local machine, or it is the same thing. So here I'm saying, okay, I want to start this computation by year. I'm gonna partition that in 20 years. And this is a very simple, embarrassingly parallel, what it's called embarrassingly parallel. So we can parallelize, use the cloud and taking advantage of AWS capacity to scale. And we can do it for 1 million at a time if we want and have the money. Then we do the computation, right? So we get to this point. Let's see if I still have this in memory. I still have it. It's on 20 years. And this is the important part, I think, in my opinion. Now you can start doing like your scientific analysis. As I said, if we remove all the code to like explain other stuff, we'll end up with not a lot of Python. And then you have this. You have we're using the Pangeo ecosystem, to do some scientific analysis. We're plotting the Great Lakes. We're plotting the mean temperature for 20 years. And you can even, say, start asking the important questions like, what would be the temperature trend by region, by lake? I'm going to do a statistics, for example, on temperature by latitude, for example. So here I'm saying in 2003, what will be the distribution of temperature depending on the latitude? So if you go north, it should be more colder, and most of the temperature in the water should be on the left side. So if I go 3 years later after that, well, you see that the temperature distribution moved to the right, which is not good for obvious reasons, but that's the cool part. And we didn't egress anything in this one because everything was in region traffic. This one I executed in the cloud, so all of that would be free of charge because Amazon doesn't charge for in-region egress. Well, there's no egress. So I feel like earthaccess will be like, the library that will allow us to do cloud computing the easy way and the way that it works for Python users. And I thank to the community and the projects that make this possible, especially Openscapes for sure, the Pangeo community and its life for providing time for this development. And you see the faces of some of the people that contributed to the project. So with that, I'll share the screen with Qiusheng, a friend that some of you know.
Yeah, so I think we'll go straight into Qiusheng, unless you wanted me to walk through a few of your introduction slides first.
No, I can go directly to the demo.
Okay, great.
So let me start here. Okay, can you see my screen now?
Yep, we can see it.
Yeah, so for this demo, I'm going to show you two things. The first one is the NASA Earthdata repository. And so this one built on top of the earthaccess package, but built, made available in a tabular format that's much easier, readable, and accessible. Because when you use the earthaccess, you need to know the DOI, the concept ID, or the short name. And sometimes users don't know where to get that one. So I kind of created this repo using the earthaccess package to retrieve the list and then present it in a TSV. Basically, it's just a CSV, but it's tab delimited, also a JSON format. And it's being run automatically every 24 hours. So if there's any updated data set in the NASA Earthdata, you will be showing up, either it's typo or new days or something like that. So, and if you download this file and then open it on your local computer, it will look like something like this. So this is just a tabular format. And so you're going to have access to, for example, the short name, DOI, concept ID, something like that, and some of the basic links. And if you scroll down all the way to the end, I think it's roughly almost 9,000 data set in total. And the reason I built this one, because I want to build on top of this to allow user to source data without having to remember the name or worry about where to get those concept ID or the username. So once I have this one, and then I integrate it into the leaf map Python package. So for those of you who are new to have not heard about leaf map, is basically just a Python package for doing interactive visualization of all kinds of geospatial data or vector data, raster data. So and specifically, I integrate into leaf map with the functionality that allow users to search the Earthdata catalog directly within a notebook environment. So I also send the link in the chat. You can check out this one. And user can just simply open, for example, in Google Colab or implant it to the computer, and then they can just install the package. And so the authentication are pretty much the same as what Aaron and Luis introduced earlier. But it makes it a lot easier because you don't even have to do coding. You can just create a map and then load the interface. So next, I'm going to show you how you can actually utilize that. So this is a notebook, for example. Again, you can run in Colab or you can install locally. So let me show you just within a couple lines of code, you can import a library and then you can use the login. So this is the same method using the earthaccess login. If you have the net.rc file, or you can just pass in the username, password. And this one here shows you the table, basically the data catalog I showed you earlier. In total, we have 8,952 data set in the NASA Earthdata catalog. And then, for example, you can use the same thing to search the data. And so this one shows you, for example, I'm going to search the jet data, and you can pass in, for example, a bounding box and also a temporal, basically a time span. And the nice thing about this is you can return the data set in a geodata frame. So in that way, you can visualize that besides return as a list. So this one here shows you directly what the data set look like. Okay, so this is, for example, all the footprints intersecting with the area of interest. And when you hover your mouse, you will see the pop-up, basically the information contained within each one. They are locked up footprint in here, but you hover your mouse, it's going to change dynamically. There are lots of information, so but it's kind of built on top of earthaccess, makes it easier. And you can also download the data easily. For example, this one returns 259. If you want to download the data, you can. So here I can just simply, for example, download the first 5. I've already downloaded, so it's not going to re-download again, but you can clearly see how big is the data set. You can specify where you want to download. So just one line of code, you can get the result. So this is still, I mean, similar, unique couple lines of code. And the next one I'm going to show you here is even easier. So I just import the leaf map package and then just one function called to add the NASA Earth data interface. So this is what it looks like, pretty simple. So essentially, you just need one line of code. Once you create a map, you add the interface. So this is the one here showing up on the right. And so let me quickly show you, right? This one, you can hide it if you want. You can click this button. If it's too overwhelming, you can click here. It's going to keep this one. So this is the simple map. You can also maximize if you want. So it's directly within the Jupyter environment. And then you can start searching any data set. So again, this whole list here is the one that retrieved from that data catalog, that tabular format that I showed you earlier, right? And then if you know specific data set you want, you can search, select any one. Any data set. So for me, for example, I know I'm going to find some nighttime light data. You can just search nighttime, hit enter, and then you will be able to see all the lists that relevant to nighttime light. And then you can select, for example, I want to select this one. You're going to show you the short title. So basically, all the information is from that spreadsheet. And then you can zoom to anywhere you like. So here allows you to use the map area, so the map view based on the area of the map right now, or you can just pass in the coordinates of the bounding box, the min x, min y, max x, max y if you want to. And then you can also specify the date if you want to. But for me, I would just like to find out, for example, what are the nighttime light intersecting, for example, in the US. And then you just search nighttime, select what you want, and then just click search. You see, quickly within less than a second, you get some of these. It's not fully coverage because you need to change like the maximum item. By default, it's return only the first 50 items. And then if you hover your mouse, if you click, you will be able to show you, for example, what data set, all the metadata of the footprint intersecting with this one. And you can download the data. You can also see, for example, from the list, you can select, if you know the specific one, you can select it. So this is one example you can do, but you can also, for example, I can reset. And for example, I want to try down the JEDI data. Similarly, you can search it, and here I can search whatever JEDI data that you want and click this one. Similarly, right, I can zoom to anywhere you like. And for example, here, then just click search. Again, you can search the date if you want. You see, very, very fast, and there's no coding. So it's kind of one step forward built on top of earthaccess. So now you can see the footprint. You can click that, and you can see all the metadata information. You can see all the tiles that intersecting with the area. So this is more makes it easy for user to figure out the data set, similar to the Earth, like NASA Earthdata interface, but this is integrated on the Jupyter or the Python workflow, so that you don't have to leave this interface. You can get everything done within the notebook. And if you want the result, you can also access the entire data frame. So whatever being searched and returned on this map, you can access that in a geodata frame, basically in a tabular format. And inside there, you can get all the information, the grain new, the ID, and also the link to the S3 bucket. So all the 50, for example, the first 50 are being returned in here. And if you want to download the data, you can just call this one line, and then you can download. For example, I'm going to download the first read. It's going to take some time, but I'm not going to download it, but you can try it out. So this is basically a very easy way for you to search the data interactively, pretty much without coding, and then with the interactive graphical user interface, you can visualize the footprint. And so next one I will show you here, this is notebook number 90. This one shows you how to visualize the data interactively. You can visualize, use LeafMap to visualize pretty much all kind of raster data and vector data. So here, this example, I'm going to show you how to visualize some raster data. And if you're using Python packages, most likely, most of the time you just print out a thumbnail. But LeafMap support any data in the cloud, also data locally. So the first one here is visualizing a cloud optimized GeoTIFF, right? So this one here is a cloud optimized GeoTIFF stored on GitHub, and you just need the link, and then you can just pass in at the code layer, and then give a name, and then you can use the inspector. So here, this is a cloud optimized GeoTIFF that has several hundred megabytes, and you can see, you can also, for example, you can turn on the tool, you can turn the data layer on and off, and you can change the opacity if you want to. You can zoom in to see more details. So these are all the ways that you can visualize data interactively rather than print out a thumbnail. You can also visualize, for example, the spatial temporal asset catalog. Again, you just need the URL to the JSON file, and then you can visualize that pretty easily. Same thing, you can also change the opacity. Besides those traditional cloud optimized GeoTIFF and spatial temporal asset catalog, you can also visualize data on the Microsoft Planetary computer. I also have the other package called Gmap, is for Google Sending, but this one, for example, you can visualize any data in the Planetary computer catalog easily. For example, you can zoom in, you can zoom out. You can also do some simple calculation if you want to. So those are basically visualize data in the cloud. Of course, you can also use that to visualize NASA Earthdata if you have the direct link to the data set as a cloud optimized GeoTIFF. If you download the data to a local computer, this is what it looks like. So I'm going to download, for example, a simple sample Landsat data to my local computer, and then just one line of code, you can visualize the data, and you can use whatever band combination you want, right? So this is a simple Landsat sample data, and I'm going to visualize using near infrared, and you can set the minimum, set the maximum. It's going to look like this. And like I said, you can turn the layer on or off. You can change the opacity. You can also check the pixel value. So for example, if you just hover your mouse, if they click on the map, it's going to be able to query the pixel values. So this also works for the cloud optimized GeoTIFF anywhere. So you can click your mouse on the map, you will be able to get the pixel values. If you just want to get the visible band, you can click, for example, just the 4 band, the 3 bands that being displayed on the map. And even better, if you are doing, for example, classification, you want to do machine learning, you can also collect training samples, right? So for here, class label, I can say, okay, I want to collect some forest labels. You just click your mouse on the map. Of course, you need to zoom in to see more detail, but here I'm going to quickly show you, for example, I click some of these forests, and that after that, okay, I want some water labels. I can zoom in, get some water labels here. If you zoom out, it's going to cluster into a cluster. For example, I get a couple more points, and then you can just simply click the download button. So this one will be downloading to your computer, and so for example, I'm going to save this one to my downloads directory, and then on the left side here, right, once it's downloaded, I can show you quickly what it looks like, right? So this is the one that I just downloaded. You should be able to see the spectral bands in here, 1, 2, 3, 4, the location of the points, and also the label. So this makes it easy for users to collect training sample and then just do things interactively. Last one I'm going to show you is basically showing you can also do analysis, right? So you have a Landsat data, and then you can use raster IO or X-array to do analysis. So here I'm just going to do a simple NDVI calculation, and then you don't need to save the result. So LeafMap can visualize the data in the memory. So just showing here, I use the Lancet data, and then I don't need to save the result. It's going to generate the raster data, and you can visualize that interactively. So similarly, I can do, for example, I can, stop here. So I can also, for example, NDVI, I can click my mouse on the map. You can also see, I can query the pixel value. So you can do for physical file, also files in the memory. Similarly, you can use X-array, right? I have a simple DEM, and then I want to classify the DEM into 2 classes. Or the first one is, for example, elevation greater than 2000 and also elevation less than 2000. And you can visualize that interactively. So take a look at this one. So the original raster and also the one after classification. And again, it's the data in the memory. So it makes it easy to visualize. And last one is if you want to compare the data side by side, you can pretty much also use just one line of code, and then you can see things interactively. You can zoom in, you can zoom out. So this makes it easy for you to visualize data. This notebook only shows you the raster data, but there are tons of other notebooks on the website. So you can, for example, the jet data, vector data, all kinds of data. So I don't have time to go into detail. I'm already over time. So if you have any questions, I'm happy to answer your questions later. Thank you.
Great. Thank you so much, Qiusheng. All right, well, I'm gonna wrap things up with, get my camera going, with just a few final slides here, and wanted to make sure we had some time for Q&A. I just want to, and thank you all so much for presenters, and I do just want to emphasize the fact that this sort of collaboration and sort of utilization of earthaccess to broaden that accessibility of Earthdata in other commonly used Python packages. Like, again, this really speaks to that community element, and Openscapes kind of providing that venue for collaboration. So there are so many other examples of other ways that we've been thinking about how to broaden that accessibility. So there's examples with Earthdata login as a new CRAN package in R that was also sort of leveraging earthaccess. Some ways we're incorporating it into MATLAB workflows as well. So there's really countless examples here. And really just to wrap up, you know, Luis already highlighted a couple of really exciting kind of upcoming features. There's so many more that are listed under the issues and discussions of the GitHub repo. So these are just a few, but so many other ideas, again, across the DAACs and our user communities. Things like a command line interface. We know, again, that we want to expand and recognize not everyone are Python users. Aligning earthaccess with Stack. And then also there's been a lot of recent kind of conversation and discussion around kind of this ability to hook services into that earthaccess workflow with Harmony and other kind of utilizing sort of a plugin interface to connect with other tools. And then things like improving the kind of EULA UI UX, which again kind of comes from our direct user feedback. So more to see here. I really just want to end with, you know, how to connect with us. We have been kicking off bi-weekly hack days that are every other Tuesday from 11 to 1 Mountain Time. We're trying to foster new contributions. You do not have to have a background. You don't have to be a software engineer, have a background developing earthaccess to contribute and be a part of this group. So please reach out in GitHub. We have an announcement kind of chain and ongoing discussions for more info. And want to acknowledge again all the contributors that that have been a part of this community thus far. And just wanted to end on this really great visualization, and to end with the fact that, you know, reproducible science with less code makes open science more accessible. So with that, we'll open it up for Q&A. Thank you.
Wow, thank you all. This was amazing. I could probably gush about it all afternoon, but you guys have really had an outsized impact on open science and kind of taken things that last mile to actually get to the users. And it's pretty incredible to see all the stuff that we built over the years, like just kind of gelling the way that you guys have made it gel. So with that, I haven't seen any real questions go by that haven't gotten answered in the chat. Looks like people have been engaging pretty well. But if there are any questions, please raise your hand. Oh, I see Andrew Johnston has his hand up.
Hi, Andrew Johnston, ASF. I'd just be curious to hear if you have any feedback for the DAACs, like during your development process. Is there anything we can be doing better to support these kinds of workflows? It's a big question. Just encourage you maybe to forward those thoughts as you encounter them.
I can quickly provide some feedback based on the tabular, like the spreadsheet that I built on top of the earthaccess. I think the issue I encountered was some of the metadata was not quite consistent. So there are lots of like missing. When you open the CSV, you will notice. I think there are some typos or some like missing data, and it's not quite consistent across like different decks. So there might be something that can be potentially improved in the future. I don't have a list of all the things, but sometimes you saw some data, they might not necessarily have the same metadata, so it's not consistent. So it will throw some errors on the leaf map package. I will find out and I will get back to you. Yeah.
All right. Any other questions out there? Okay, well, while other people may be putting their hands up, Luis, I had one for you. I didn't see a timing on what you were able to do with your coiled example, and kind of blowing that query that you're doing out over a longer time series. But
my internet is kind of flaky now. Can you repeat the question, Patrick?
Yes. So what was the timing like for the example that you did with coiled and the longer time series?
It was 8 minutes, and actually 4 of those 8 minutes were just the provisioning of the machines. So it's way less than that. And the cost is in the cents, so like 0.04 cents, the cost of like the cloud computing use.
And that was like a daily time series over an area for how many years?
20 years.
20 years. That's
yeah. It is the same analysis that you did for your library, and kind of like I've seen it. I don't know who started it, but it's a Great Lakes and uses Muir.
Cool.
I'll just mention, I think that I'm trying to look at questions too. There was a question from Alex Gardner on kind of future funding, which is a great question. I don't think I have a clear answer, but I did want to really just point out again the fact that this is sort of being developed within existing kind of allocations, at least speaking for the NSIDC DAAC, as like with our time as Openscapes mentors. So there is kind of that element being tied to our involvement and Openscapes kind of, again, helping to enable this. And I think that's, likely the same as we've seen from other DAAC contributions, and those hack days, which have been, we're facilitating those through Openscapes as well. So we've seen that time from at least our DAAC developers, are kind of from those Openscapes mentors. I think that's not fully like the case, I think, for everyone though. And I think there's other people kind of outside that who have been contributing. But that's just one element that I just wanted to speak to in terms of kind of funding. I don't know if anyone else has any thoughts there.
So no thoughts funding wise, but maybe a related question. Are there places where, when DAACs are standing up endpoints or doing things that they might be triggering configuration changes or those kinds of things that are necessary on the part of your library? I guess I'm asking, for the developers that are on this call, at what what are some of the touch points that maybe they should be considering, do this ticket and then go issue a pull request to earthaccess?
So, I mean, Luis, in terms of like the kind of like our dependencies, right, on those API libraries. I mean, I know like we're utilizing the CMR Python library, but like I'm trying to think. I mean, I feel like it's robust in terms of when there's changes made. I think there would have to be pretty major breaking changes to impact earthaccess. Is that true?
Yeah, we have some tests in place, and the library itself is very lean in dependencies. So I don't think there is something that will, break the library. And one of the cool things that we've been doing and will continue to do is like in the integration test, we're testing that we can actually access some of the most obscure data sets. And we always have like a random failure because this particular data set is behind this other custom endpoint from a DAAC. And we noticed that. So I wish we could have like a full test that will test everything, and it will tell like these 10 data sets have an accessibility problem because of this and that. So that's something that we'll have to consider doing in the near future. But I don't think there is anything unless like CMR changes completely. I don't think there is any major things. Yeah.
And Catalina just asked if earthaccess works on data sets that are in a UAT environment.
Soon. That's actually in the works, and Danny, if Danny's here, he's working on that too. Yeah, that's coming really soon. Yeah, and another thing that now that I see Joe, ASF had some of those like custom endpoints, and now they're working. So a user that works with Sentinel-1 or something reported like, I cannot get to Sentinel-1 data with earthaccess, and we fix it like in a week or so.
I think the benefit of something like earthaccess is that the DAACs can all come together in kind of an open spot and figure out how to kind of solve those access patterns. Doing kind of a comprehensive access review quarterly or yearly or something is a great idea. In terms of funding earlier, there is a couple ROSES calls specifically for open source software and whatnot, but they don't have dates yet or aren't being called this year. So things like ROSES and potentially NSF grants for access as well on the software side is potential that Louis and I have been looking at.
Okay, we're coming up on the hour, and I don't see any other hands, but I'm sure these guys would be willing to answer questions offline if you have them. Thank you all for attending, and we'll see you next month.
Thank you, everyone. Take care.
Thanks.
Bye-bye.
Thanks. See ya.